name is Kaylee Champion, and this is Electron Beam Properties for Touchless Potential Sensing of Complex Geometry Spacecraft to be presented at SciTech 2024. So there is plasma everywhere in space. And when a spacecraft is placed in a plasma environment, it's subject to different currents that may result in a charge or a potential on the surface. And the magnitude of this potential varies depending on the plasma environment. So shown in the plot on the right, in general, as the altitude of the spacecraft increases with respect to Earth, the hazard level for spacecraft charging becomes higher, or the potential expected becomes higher in magnitude. And as you can see, specifically in GEO, the hazard level is very high, and we can expect potentials on the order of tens of thousands of volts. And this potential can be dangerous because if different potentials build up on nearby surfaces, there can be an electrostatic arc discharge, or essentially a small lightning bolt between the two surfaces that may fry components or ruin electronics, and has ended spacecraft missions before. Arc discharges can also occur between two spacecraft that are docking, and two charged spacecraft going through rendezvous and docking operations may exert unexpected electrostatic forces and torques on each other. Now, in addition to these detrimental effects, electrostatic forces have also been looked into as a method of electrostatic actuation. So essentially, a servicer, or a spacecraft that we are in control of, is equipped with an electron beam that it then aims at a target, so a piece of debris or a client. Since negative electrons are being emitted from the servicer, it charges positively. And since negative electrons are impacting the target, it charges negative, ideally. And once a positive and negative charge are established on the two spacecraft, and a positive Coulomb, or electrostatic force, is also established. And this force can be used to tug debris into a safer orbit, or even detumble a spacecraft without ever having to touch it. Before we can account for these detrimental effects or utilize electrostatic actuation, we need to be able to determine the potential of the nearby spacecraft. So two of the methods we've looked into in order to do this are the secondary electron and X-ray method. So in order to use these, an electron beam is once again aimed at a target and utilized to excite X-rays and secondary electrons from the surface. The energy of these emissions can then be read by the servicer and used to determine the potential of the target with respect to the servicer. And several different methods exist to determine the potential of one's own spacecraft and have been used in previous spaceflight. So once we know the potential of the servicer, we can determine the potential of the target. Now, there are different pros and cons to each of these methods. Secondary electrons are more accurate when utilized. We can determine the potential on the order of tens of volts, whereas X-rays is more on the order of hundreds of volts. Secondary electrons are favored by lower energy electrons, which means that we can use a lower energy electron gun or addition, there is a strong dependence on the deflection angle of the beam. So as you notice, the ideal spot to hit seems to be a deflection angle of +2 in both the X and the Y direction, or hitting that top right corner of the main body of the target. And if we're not hitting in that region, regardless of the beam energy or of the half angle, we're probably not going to be able to send secondary electrons. However, the region or the number of deflection points in which we're close enough to that optimal position that we can detect something increases as the half angle increases and as the beam energy decreases. So we know from this that we want to maximize the half angle of the beam or make it as wide as possible so that we have a better chance of hitting that optimal position on the target. And we want to decrease the energy so that the yield of secondary electrons is increased. Now, the way this is actually implemented is essentially a deflection point is picked. And then at that deflection point, the beam energy is swept through until it's determined that we can't sense anything at this deflection angle, or we actually sense enough secondaries that we can determine the potential. And the initial guess is a little bit tricky. Ideally, the beam would impact the target with a potential of about 1 kilovolt. But if you don't know the potential of the target, you can't really ensure what energy the beam is going to hit the target at. So we have some initial guess, and then we'll increase the energy until we either sense something or until we've gone through the entire range of energies possible. And then if it's determined that nothing can be sensed at that deflection point, we'll deflect the beam and try again. And the initial deflection angle will be 0, 0 if there's no prior knowledge, or whatever the previous deflection angle was that worked at our last measurement. And then the distance from our initial guess is increased until we've gone through the points or we've sent secondaries. So in this plot on the right, you've got an example of the deflection path the beam might follow. So we're starting at 0, 0. You got that light blue dot in the middle. And that region of the graph is not very bright, but we're not detecting very many secondary electron currents. So we'll have to deflect the beam again. And the next spot is that deflection angle of +1 in both the X and Y direction. And as you can see, this is a region in which we're detecting over 100 nanoamps of secondary electrons, which should be sufficient to determine the potential. And so we would stop there and be able to move on. Now these plots again show the detected X-rays for various beam properties. There is not as much of a variation with these. The beam is impacting the target for all the deflection angles. And that slight variation color is more likely due to noise in the simulation than to anything physical actually happening. And also as the half angle increases, the photons detected is not significantly changed. Now the main influence we see is that as the beam energy is increased, the magnitude of detections, the magnitude of photons per second detected also increases, which again follows X-rays prefer higher energy impacting electrons. So all we really need to do is maximize the beam energy and try to hit the target. So these beam controls are tested in a docking problem. So previous work enabled calculation of trajectories for docking that minimizes the electrostatic torques on a target. So for this problem, there will be an initial separation distance of 60 meters, and then the distance will be decreased with hold points at 20, 10, and 3 meters. And the trajectory that the servicer will follow and those different hold points is shown on those 3 pictures on the bottom. These pictures are shown using the multisphere model. So the multisphere model essentially discretizes spacecraft into several spheres to allow for fast calculations of electrostatic forces and torques. Now the servicer is initialized with a potential of -4 kilovolts, and the target is initialized with a potential of -13 kilovolts. And then both spacecraft linearly approach -8.7 kilovolts over the course of this entire docking problem. So the potentials are changing, the relative positions are changing, and the separation distance is changing. And we want to see how this electron beam manipulation works in this scenario and how long it takes to get detectable currents or photons per second. So these graphs show the final beam properties and the time it takes to get the emissions for both the secondaries and the X-rays. So as you can see for the secondary electron emissions, It can take anywhere from about half a minute to quite a few minutes. At that 20 meters of separation, the deflection angle has to be changed twice. And so we're sweeping through several beam energies and then sweeping through several different positions. And so it takes almost 20 minutes to find the correct beam properties that allow us to detect secondaries. However, once we find that ideal beam deflection, it seems to work fairly well for the following positions, and we're able to detect secondaries much faster. And then for X-rays, those are faster in general than all the secondary electron positions. We see at 20 meters, again, the beam has to be deflected, so it takes a bit longer, but we still find that in a little over a quarter of the time than it takes to find the secondary electron emissions. So to fuse the two methods, it's useful to first find X-rays to get a rough estimate of the target potential, because this allows us to set the beam to an ideal energy to generate secondary electrons. And then we can sweep through the deflection angles, holding that energy constant until we find secondary electrons or we realize we can't detect anything in that position. And so the final beam properties again, and the total time is shown for this. So as we can see, the total time does not increase significantly from when we use just X-rays. The change of time is about 20 to 50 seconds. Which means that we may actually be able to utilize both X-ray and secondary electron emissions to get accurate measurements without making a huge sacrifice in the time it takes to get those measurements. And something else interesting is that we were able to detect secondaries at all tested positions, especially since prior work indicated that secondaries may only be detectable at like 10% of relative positions. So there are two things that may explain this. One is that altering the beam properties does allow us to detect secondaries at more locations. So we do see that's happening in these bottom graphs shown. So the one on the left shows the detected secondary current when the beam is held at 0, 0 or no deflection. We're not attempting to change it. Whereas the one on the right, the beam is deflected such that the secondary electron current is maximized. And we're obviously able to detect more current when the beam is deflected versus when it's held constant. Another explanation for this is that we just happen to be in positions where we could detect the secondary electron emissions. And as I mentioned, the trajectory was designed such that the torque on the target was minimized, which means that there may be some sort of relationship between the torque and the detected secondary electron current. So these plots down here show the torque on the left, where the red represents smaller torque, and then again, the detected secondary electron current on the right. And as we see, there does seem to be some sort of rough relationship between the detected secondary electron current and the torque. The torque is minimized towards that bottom right section of the graph, and the detected secondary electron current is maximized, which is exciting because this means we don't need to sacrifice, which means we're able to, which is exciting because we're able to minimize the torque on the target and detect secondary electrons at the same time. Or we can even minimize the torque on the target in order to find regions where we can detect secondary electron currents. So in conclusion, fusion of both X-rays and secondary electrons allows for increased accuracy in determining the potential of a target without making large sacrifices in time. And there may be a relationship between the minimal torque on a target and the detected secondary electrons. Future work is to further explore this relationship and to validate the controls and the torque and sense electron relationship for differentially charged spacecraft. Thank you.